Does everyone think this is like audience participation? Okay, here's what Bohr was able to do. His model got around the problem of centripetally accelerating charges should lose electromagnetic radiation and energy and spiral into the nucleus, and no mass should exist. And he looked at the emission spectra of excited molecules and atoms, and he figured out what was going on. He suggested that here's our little nucleus here with a couple of protons, couple of neutrons. This is a very simplified model. Let's suggest that the electrons can exist only at discrete fixed orbitals that correspond to a certain energy. Okay? And electrons could exist only at these fixed energy levels or fixed orbitals. Okay? What we will see is the further you get from the most strongly bound level, the further you get, the less potential energy you have, the closer you are to being liberated. This agrees with what Einstein said about the photon coming in and striking the least bound electron of the polished metal surface. So he said, okay, they can't just exist anywhere, because if they did, then we would get continuous spectrum from our gas discharge tubes. But because we're getting discrete, it's that the electrons are making jumps. They are making transitions. That's a better word. Don't use jump. That is too colloquial. Just like the electrons suffering. No, they didn't suffer. So, your electron can make a jump. It would require a certain amount of energy, just like lifting a ball from the ground, placing it onto the table. When it falls back down, that energy must be released as a photon. Energy of the photon, which is equal, let me write that lower because students are going to wonder what that means. Energy of the photon equal to HF, which corresponds to the energy of level 2, subtract the energy of level 1. Okay? So this is conservation of energy. If we said if a ball fell from the table to the floor, you would say, well, there was an mg delta H that must have been converted to kinetic energy. Heat, sound, motion. So I'm trying to put the analogy to classical mechanics, but the analogy breaks down because it's like the ball just suddenly, instead of slowly accelerating to the ground, it just goes from there to there without in between and outspits energy. So it would be like ball goes from table to floor and a big thunderclap of sound comes out, equal to mg delta H. Okay? So this is the strange thing. It's like saying the electrons exist like rungs on a ladder. Your feet can exist only on a rung of a ladder and nowhere in between. This is where things get weird. How can an electron go from one point in space to another point in space without ever existing in between? But it does. Okay? And the next thing is, providing you are constantly putting in energy, the electron doesn't have the photons stored in it like a reservoir of photons. It's if there is energy being put in and it falls back down, it will just continue pumping out those photons. So that's what's happening over here. Well, there's a few things going, but you've got electrons racing through from one side of your electrode to the other. They gain the kinetic energy that's equal to the voltage. But as they race through this low pressure vapor, they're going to smack into this atom. Okay? So there is going to be an incident electron flying in, and it might collide with an orbital electron and it might knock it up. And then as it falls back down, we see that energy. So we are essentially converting electrical energy into kinetic energy. That kinetic energy then goes into light. Okay? Now let's just, on the other side of this diagram, let's just say, what about something that went from level 3, an electron dropping from level 3 to level 1. Well, that would have to put off more energy because there's a greater jump. So in this case, with greater energy, you would have a greater frequency. All right? Now have a think. If we looked at hydrogen, we were seeing red wavelengths being emitted and blue wavelengths and violet wavelengths. All right? So he was the person that put it together that wavelength is the difference between energy levels. So it's this massive puzzle. He was given all of the differences of the energy levels, but not the energy levels themselves. So he had to try and figure out where the energy levels must be such that the transitions that occur are what is observed in your spectrometer. Yes, Edibar?
So how does the electron emit a photon when it falls out?
So we're going to look at the standard model towards the end of the term. Basically, there is a fundamental interaction between photons and electrons. Okay. In fact, electrons, this gets a little bit crazy. Electrons can exert forces on each other, and if you brought two electrons together, they would recoil due to their charges. All right. A deeper understanding is that they're actually transferring mediating particles that mediate the force. That particle is considered the photon. And so as a photon is ejected, if it has momentum and energy, it's because it came from the electron. All right. It's getting a little, again, this is where stuff gets strange. But if an electron changes its momentum and its energy, then it's either colliding with another electron or emitting a photon. Okay, I'll stop the definition there because it gets quite deep and philosophical. So, I would like you to recall the 4 postulates that Bohr put down to his model. Go on, you had your hand up.
Blue light has a higher intensity or a higher frequency?
Higher frequency.
What's the difference between frequency and intensity?
Well, intensity is how many times it's occurring. Now, did I show you this yesterday? Yes. Okay. So, we will tie this back in. That we saw that through the spectroscope, but our eyes could not measure how many of each. Okay? Brightness doesn't work because our eyes are not as susceptible to blue and violet. We're more susceptible to the red side. So, generally, you would see the red being brighter. Okay, all things being equal amounts of photons, you would see the violet dull and the red bright. But that's just our eyeballs. Coincidentally, there is more red and less blue and less violet. There is a probability of where an electron... Yes, it's a probability. You're more likely to see transitions of a certain level or to a certain level than others. Okay, we'll get to that maybe tomorrow. So, I would like you to consider the postulates at a year 12 level. So, how do we spell Bohr? B-O-H-R. Now, I'm going to put 3 down, and we're going to need some space. So, have a look at the space we've got here, and I'll try and write proportionately. In atoms. There are, okay, thank you. Yes. There are fixed energy levels that electrons exist in. These correspond to a fixed distance from the nucleus. Okay? The closer you are to the nucleus, the more strongly bound, the deeper you are in that negative potential well. The further away from the nucleus, the less bound you are, the closer you are to having zero energy. We spoke about negative energy when we looked at gravitational potential. Remember I said if I gave you the escape energy to be free from the Earth's gravitational field, but no more, I just gave you just that amount. You got to an infinite distance and now you're stationary. Technically you have zero energy. If I gave you all of that escape energy plus 10 joules, then you would coast off for the rest of eternity with 10 joules of kinetic energy. So we're going to see that these energy levels are going to be negative. And to free an electron, we've got to get it to energy equals 0. Okay, so don't be freaked out when I show you negative energy levels. Next. When an electron makes a transition, okay. We could reverse that postulate as well to say if an electron moved to a higher level, then it must gain that discrete quanta. Okay? Last one. Oh, now I'm going off the script here. This energy okay. So this wait, that's a bit earlier. Hang on. This is just taken straight from Wikipedia. So if you just Google search the Bohr model postulates, obviously it's never that simple. These were really, really smart dudes and they were doing a lot of really crazy maths. Okay? So what we're really concerned with down here is initial energy to final energy, the frequency. Now, again, we're in Australia, we will use the symbol F because that Greek character looks too similar to V. So I don't want you to get weirded out that C equals V times something. Yes?
What did Chadwick do?
Chadwick discovered the neutron in 1932.
Oh, that was...
Happy days. Yes.
I thought he had something to do with that.
I hope not. So, that's the bottom one. Obviously, this difference in energy is just going to be final minus initial. That equals HF. Okay, that's what we're saying. And so he's just saying, well, the frequency would be the difference in energy divided by Planck's constant. That's just rearranging the equation. Okay? And we've said circular orbits up the top, instead of an infinity, by classical mechanics, there's only for an electron to move. Okay, so that middle postulate, we're just going to say fixed orbitals. Electrons orbit. Okay, so the first one is that the electrons orbit. Then the second one will just say in fixed orbital levels corresponding to a certain energy and a certain distance. This one basically goes, all right, it doesn't spiral into the nucleus because for it to spiral, it would have to go from one orbital, it would have to leave that orbital. And the quantum mechanics forbids that. Okay? Classical mechanics says that the electron could exist anywhere, like a satellite can exist at any height. And we can figure out its behaviour by those equations. But classical mechanics couldn't explain this. We're now down to quantum, where we're taking discrete steps from one energy level to another and never existing in between. Yes, Mr. Rahal.
So Newton's law of gravitation would be less affected in this situation?
Okay, so we are at such a close space to the proton, the nucleus and the electrons are so close together that the Coulombic force is so much more stronger than the gravitational force. Yeah, you're comparing, like, I'm just trying to think, it'd be like 10 to the negative 9 newtons of a Coulombic force, and then gravity of an electron near a proton, you're looking at like 10 to the negative 40 something. So it's like 10 to the 30 times weaker. All right, so at this level, we don't even, it's not negligible. It is negligible. We don't consider any gravitational forces on the electron. Now, I skipped a step. For a simple electron orbiting a proton, such as hydrogen, there's a really nice equation for the energy levels. Because there's just one object being attracted to another, this really neat pattern came out, and it's only for hydrogen. And here we go. It's the energy at a given n level is equal to negative 13.6 over n squared. Okay? It is a very simplification of the Rydberg constant, where you're just factorizing out the difference in energies to get a wavelength. But I would like us to consider this for the energy levels of hydrogen down here. What is that dot? Could we please write the following? Now, I need you to write nice and neat and sharp and small because we don't have much room here. That's my fault. N equals 1 for hydrogen is the ground state. And in fact, N equals 1 for any atom is the ground state. Then we're going to go up to N equals 2, N equals 3, N equals 4, N equals 5. We'll just do a little dot, 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 N equals infinity. And between then, we'll say many levels. Yes, Marcus. There are many levels that the electron could exist in hydrogen, but they are not likely to exist there. All things being unperturbed and undisturbed, they would just love to exist in the ground state. And if you start jiggling your atom around or smacking it with other photons or electrons, they might get prompted to go up. Just like things would like to be on the floor, but occasionally a kid will come over and kick something up and it lands on the shelf. Yes, Marcus. Back to his first question.
I'm sorry.
Yeah, no.
Think about the Lyman series, the Balmer series, and the something series above.
Whoa, calm down.
And I'm saying it's got the first one that says decays to ground state, and the second one says decays to n equals 1. So is n equals 1 not the ground state?
Where does it say that?
Right, just up.
All right, that's a typo. There is no n equals 0.
Okay, so n equals
I didn't notice that. My student made the mistake. Don't look at that. Look at this. Could I please get your calculators out? Could you go negative 13.6 divided by 1 squared? Yeah, there we go. So, over on this side, we're going to have energy in EV. Okay? Then, and this equation, this equation is only for hydrogen. As soon as you add an electron and an extra proton, stuff gets weirder. And you cannot get a nice, simple equation. In fact, the electrons, as there's more and more electrons in different levels, they start to interfere with each other, and you get these weird effects where the lines start to split. It's called the Zeeman effect. The electrons have different spins. So we can look at a very simple atom. And this is the simplest one that we have, and we can play with that. Could you please do negative 13.6 on 2 squared?
Negative 3.4.
Could you do negative 13.6 on 3 squared? Could you do negative 13.6 on 4 squared?
0.85.
And then lastly, negative 13.6 on 20. 5 squared is 0.514. Okay? Now, this is what Rydberg noticed. Obviously, I haven't drawn the energy levels to scale, but the distances in energies between subsequent levels start to approach 0 as n approaches infinity. And that was observed, as we will see, if you look at the transitions, as the transitions come from, or start to go from higher levels up to infinity, they get closer and closer together. And we'll see how that manifests itself in the emission spectra. Now, over the page... Oh, no. You've got no room. Could you please find yourselves a blank piece of paper?
Scroll over to the right.
Scroll over to the right. What we are going to do, Justin, is I would like you to draw all of the electron transitions that could be made to the ground state. So if you could please draw 2 to 1, 3 to 1, 4 to 1, 5 to 1, and 6 to 1. I could do a lot of things, Mr. Rahal. Yes, Aaron. Oh, no, sorry, you can do this here. I've just realised we're going to do a couple of mathematical equations. Now, this first set of possible transitions to the ground state is known as the Lyman series. There was a physicist called Lyman who investigated the wavelengths that came from transitions to the ground state. So just underneath this, could we please write the Lyman or the Lyman series, N series. Now, if you look, theoretically, the most energetic transition would be coming from infinity down to 0, and that would emit a photon that would have an energy of 13.6. As the electron theoretically fell into the atom and basically got negative energy, you would have to spit out a positive 13.6. Now what region of the electromagnetic spectrum is that?
Ultraviolet.
Ultraviolet, thank you. So if it's not between 1.77 and 3.11, it's going to be above violet. It's ultraviolet. So these are all UV. And in fact, let's just check. Quick mental maths. What's the difference between these levels? 10.2. All right, so we're still above visible light. Now, if you have to do mathematics... Sorry, let me rephrase that. You have to do mathematics. So, somewhere over the page, I would like you to write let's go 2 to 1. E2 to 1 equals E2 take E1 equals HF. This is the Bohr postulate, that final postulate. And now we can throw our values in. So we're going to go negative 3.4 take negative 13.6. Oh, look, we get a double negative. We get 10.2 EV equals HF. Okay? And if you wanted to go any further, HC online, you could go any further from there. You could find the frequency of that photon. You could find its wavelength. I'm here to tell you that it's got more energy than ultraviolet. Its wavelength is going to be less than about 400 nanometers. That's the smallest violet photon in the visible light spectrum. Okay, so that's the kind of maths that you need to do. Anyone could look at that energy level and go, it's a 10.2 photon. But again, you've only done 1 mark of a 3-mark question. So make sure you write down all the useful stuff. Could you now, in the middle of this series, I'm going to use a very fun pen. Oh, I've been waiting. No! What have you done? Oy. I'm going to use this one now. It even behaves. It even follows Roy G. Biv. Oh, crap. All right. Anyway, it nearly did. Okay. All of the transitions to N2 are known as the Balmer series. This guy, British, it's either going to be a Robert or a Charles or a John. I mean, British people back then, if you were born a boy, you were either going to be a Robert, a Charles, or a John, or a Joseph. Balmer series. Now, oh dear. Now, this is a bit tricky. We are in two different regions in the Balmer series. Let's just look at the most energetic possible, would be from infinity down to negative 3.4. That would be a 3.4 EV photon, just beyond visible. Okay, so let's just say infinity to 2, we wouldn't be able to see. But let's go the other way. What's the difference between energy 3 to energy 2?
There's 2.
Good point. What was the value?
1.889.
1.9. A 1.9 EV photon. Hey, that's in the visible light, and it's actually down near red. Tell you what, it's this bad boy here. Check this out. Now, you would have seen this yesterday when you pointed your spectrometer at the hydrogen sample. You would have seen the Balmer series. You would not have seen all the ultraviolet photons smacking your eyeballs. Sorry about that. And you wouldn't have seen the infrared. But you would have seen this red one. That is, look at this. H alpha, transition N3 to N2. All right, so this diagram is telling us that this is the 3 to 2 emission. Okay, and it's also telling us that, oh no, it's not. Let's figure out its wavelength. Okay, have a guessy, it's about 650-ish. Let's do some maths. So let's go over here and let's go E3 to 2 equals E3 take E2 equals HC on lambda. And now, Mr. Handler, oh no, I've got the values here. It's negative 1.511 minus negative 3.4. So we'll just do a little sidestep here. We get a 1.89 EV photon. So therefore lambda equals HC on E. Because we have our energy in EV, I'm going to use Planck's constant in EV. But please remember, this is not in the data sheet, so you would have to do that little side mission of converting. And our calculator says 6.57 10 to the negative 7 meters, or 657 nanometers, okay, which is definitely red. Yes, Justin?
So is that cyan, blue, purple, violet that we see, is that say N3 to N1, like still higher
Hold on.
N3?
The visible ones are all going to 2. This is 3 to 2, which is this one. The next energy is 4 to 2. It's that one. Okay? So yes, can we now label, this is what I was going to get us to do, which Justin is rightly looking at, that cyan one is going to be N4 to N2. Then this one is N5 to N2, N6 to N2, and then N7 to N2. And that it's just getting to the edge of what we can see with our eyes. Okay? And we haven't calculated it. What we could do is negative 13.6 over 7 squared minus negative 13.6 over 2 squared. That, we didn't figure out what the energy level of N7 was, but we could calculate it. Yes, Alex?
We can only see the Balmer series.
Half of it. Well, not half of it. Obviously, anything above N7 is now just outside in the ultraviolet. Okay? So you could figure it out. Remember our eyes kind of stop at energy levels of 3.11. So this one's getting up to about 3 EV. Okay? Lastly, the transitions to the N3. Let's draw them here. Thank you, Mr. Rahal. I will fix that. There we go. Happy? Yes. This one here is the Paschen series. And obviously the last thing that I think I inhaled a fly. I don't know what's going on. The last one that I need to label is infrared, visible light, and ultraviolet. Okay? Now, hydrogen is the unique one, and we get this lovely shape. Obviously, if we were to follow on, then each subsequent transition to N2 is getting closer and closer to some maximum. And the difference between the two is approaching zero. If we were able to see into the ultraviolet, we would actually see that it kind of, what's the word? It gets closer and closer and closer and closer and closer, and then it ends. It converges to an end point. And so some atoms will demonstrate this if they have a nice, unique energy level, that there's a sharp end and then a fuzzy end. The fuzzy end is because you've got, as you're approaching N infinity, you're getting more and more energy levels that are existing closer together, and then they get to the last one, possible, which would be an electron coming from infinity down to, in this case, N2. Yes, Justin?
What is the highest observable end state that we've gotten for hydrogen that we've observed? How close to infinity have we gotten?
How precise is your spectrometer? Remember, obviously, if you had a very imprecise spectrometer, it would be blurry. If you could get a really precise one, you could almost zoom in and say, well, it's not a blur, there's actually 20. And then you could say, well, actually, we get it even more precise, it's actually 200.
So what's the highest precision that we've ever gotten?
Not really sure, to be honest. No one's ever asked. But all of them stop at not a 13.6. All of them would stop at a 3.40. Because to go from 0 down to 3.4. Now, again, there's been some contention in the West Australian Society of Teachers, I just made that society up, as to whether you draw a transition down from N infinity. Because often, something will cause the electron to be excited, and then it will fall back down. And sometimes you would be asked to draw all of the possible transitions of that electron. And so we'll just put here, note, do not draw a transition from N equals infinity. So can you just write at the very bottom,
Do as you say, not as you do.
The argument here is, if an electron is promoted to N infinity, it's gone. It's not hanging around. Okay? If you gave an electron 13.6001 eV, and your knowledge of conservation of energy would be, it then travels off with 0.01 eV, it's traveling thousands of meters per second. Okay? So it doesn't hang around there with zero energy and go, you know what, and then sort of dive back into the atom. Okay? So you've got to be careful. And you'll notice, I just did that this year, I'm going to keep doing that. You'll notice in past WACE exams, they get around it. They won't let you get up to N infinity. They might give you energy to get up to N5, and then they go, from here, draw the possible transitions. Okay? Or it might just say, sketch in the possible transitions that an electron could make from N5. Okay? Oh, look, there's room on page 28. Oh, turn over the page. You could have written that there. Who wrote it there? No one.
I did.
Well done. You got one note. That doesn't count. All right, just here. Let's talk about that.
So we have it.
Obviously, again, they will often say not to scale, but they'll typically try and draw them of increasing gaps and hopefully parallel and straight lines. N equals 1, N equals 2, N equals 3, N equals 4, N equals 5, and we're not going to worry about anything above. Now, let's do an example. So the question might say, draw all of the possible transitions an electron could make from N equals 5. What I would suggest you do there, just like we drew the Balmer series and the Lyman series and the Paschen series, so you don't lose any, draw every single transition to the ground state first, then every single transition to N2, then every single transition, oh, I've missed one, to N3, boom. And that way you won't miss any. Oops, oh dear. Draw all of the possible transitions an electron could make from N5 to the ground state. Now, again, if it says from N5 to the ground state, that's all the possible transitions.
But you're not going to
But-
yeah.
Yes, I am.
Isn't you're hitting n equals 2 for the
Sure.
series.
Couldn't it go from 5 to 2 and then 2 to 1?
Oh, so you can use the same arrow.
Yeah, so here's where you've got to be careful. If it just says from N5, then that's a different question. So, okay, if you've got the room, this could be from N equals 5 to ground state. But if it then says from N equals 5, that's a different question. That's just going to be this one.
Wait, but that doesn't
Okay.
take it to the ground state.
No, but that's the possible transition. So can you see how the dot is the period which stops the statement? Okay.
So one on the left is from N equals 5 to ground state.
Hang on, let me just get this labelled. So just be careful how it's worded. So if you're going from a level to the ground state, is it n factorial? Is it 5? Help me out, maths nerds.
N
It's-
one. N
Is it 4 plus 3 plus 2 plus 1?
Yes.
So it's n take 1 outside of bracket factorial? No, factorial
N
is
take one
multiply.
times N take two.
I think it's
N take 1 factorial.
No,
That's multiply. So just
It's a triangular number.
Yeah.
It's the formula for a triangular
N
number.
take one times N take two and two.
Yes.
what he said. Could you say that into this microphone?
Wait, let me just check it's not wrong.
So okay, if it's n5, have a look at the diagram. If it's n5, then it's 4 plus 3 plus 2 plus 1. Okay? If it's n7, then it's 6 plus 5 plus 4 plus 3 plus 2 plus 1. You've got all of the
N
possible
times
states.
is n squared take n on 2.
Yeah.
Cool.
That's the formula.
In one ear out. I'm never going to remember that.
N.
Okay. So just be careful how the question is asked. As rightly someone said, this one here, 2 to 1, is not a transition from N5. But it could be a possible transition from N5 to the ground state. Okay? And that's the thing. We don't know which way the electron's going to go. If we get an electron up at number 5, the most likely is it would... Hang on, what is the most likely? Let's go back to our diagram. Have a look here. So this is a much nicer picture of what's being pumped out. These are all the N2. So have a look. It's more likely to get a 3 to 2, and then less likely a 4 to 2, and then more likely, less likely 5 to 2, then 6 to 2. So I don't think they would ask you about the probability of which path is more likely. Is it more likely to go straight down and spit out a large one, or it might cascade down and you end up seeing... It's too much. It depends on what's exciting it and to what state the electrons are getting to. Your population inversion, which means you've got more electrons in higher states. We'll look at population inversion later on. I'd like to just make up some values, if I may. Go. Yes, Mr. Rahal.
What's a transition?
That is when an electron moves from one state to another. The transition is the difference in energies that it spits out the photon of light corresponding to that energy.
Is that always emission or can be absorption as well?
We're not going to do absorption until tomorrow. Absorption is the arrows go the other way.
When it says draw transition, you could do either one.
No. From high to low. Okay. Just to be cruel, I'm going to make some numbers. Let's go. An imaginary atom has the following orbital levels of its electrons. And you're going, oh great, he's making them all whole numbers. Wrong. Okay? And these are all in EV. Now, you would never be asked to figure out all of them because, as we said, we've got 4 plus 3 plus 2 plus 1 is 10. You've got 10 possible transitions there. But straight away, let's just look at all of... Again, this is very similar to hydrogen. These ones are all going to be ultraviolet. Okay? Where are the visible light ones? So this could be a good question. You've got to scour these possible transitions and find the ones that have a length of, or a magnitude of, 1.77 to 3.11. Can we see any?
Yes.
Go on.
3 to 2.
3 to 2, he says. Sure, that's a 2.8. Hee. Aha. Ooh. All right, any others? What about this one? 5 to 3, that's also a 2.8. Any others? What about 4 to 3? No, that's 1.5, isn't it? So no, what? Okay, I think that was it. See, here's the problem. Students aren't taught, nor is it in the syllabus. Students are not taught about that fun number of 1.77 to 3.11 is the region from infrared to ultraviolet. But if you know that, you can quickly scour and go, well, yes, this gas sample will be emitting visible light. And some of them don't. Some of them just glow UV because all the level transitions are greater than 3.1. Some of them all glow infrared because some of them are less. Okay? Anyway, I had a fun time. Thanks for being part of it.
I had a fun time too.
Tomorrow we will look at absorption spectra. It's going to be fun. Huh? For everything. What, even infrared and ultraviolet? No. Outrageous.